So in section 6.3 we talked about estimators, and in particular we worked on this handout, which showed that the mean, the sample mean, is an unbiased estimator. Now what makes something an unbiased estimator? Well, if you remember, we had this data was our population. That was our entire huge population, right? 5 pieces of data. And there was 10 ways that we could sample and take a sample size 2 out of that population. When we calculated the mean of those samples, it gave us this column. So we got all kinds of different estimates for the population mean. Now the population mean in this case was 80. And if we average up all these possible sample means, we also got 80. Because the sum of that data was 800 divided by 10 samples gives you a mean of 80. What that's saying is that on average, the sample mean gives you the population mean. The sample mean on average gives you the right answer. Because what you're trying to do when you're taking a sample is you're trying to get an estimate of the population parameter. And if on average your if on average your sample statistic gives you the population parameter, that's what you want. And that makes it an unbiased estimator. So your unbiased estimators would include the mean, the sample mean. And likewise, another unbiased estimator is the sample variance. On average, when you use the variance to estimate the population variance, you're going to get the right answer. And there was one more unbiased estimator that we're concerning ourselves with, and that'd be the sample proportion. On average, when you use the sample proportion, it's an unbiased estimate of the population proportion. Now, what are our biased estimators? Well, you might remember one that we did from this handout, and I'm sorry I don't have the filled in version of this handout, but it was a sample range. The sample range up here is 2, down here is 5, but when we added this up and divided by 10 to get the average estimate of the sample range, it wasn't the population parameter. It wasn't the population range, which is 76 from 86, which gives you 10. So that was a biased estimator. Now, what else were some biased estimators? Surprisingly, the standard deviation. Even though the variance, which is its cousin, really, they're just, one's a square and one's a square root of the other. Standard deviation is a biased estimator. It's not that bad. We'll live with it. And last but not least, the median. These are all biased estimators. Using those on average doesn't give you what you're seeking. So, okay. Yeah, go ahead. So if you were to use the sample proportion in your data, there's hundreds or thousands of different possible sample proportions you can get depending on your data. But if you calculated the proportion for all of those, on average, that number will match the population parameter. So what's going on here is that you've got a population and a sample. So here's our population, and from that we're going to draw a little sample. And so this is our population. This is our sample. And we have things like X bar, S, and P hat. Those are going to estimate mu, sigma, and P. And on average, now not every time, but on average when you use X bar or you use P hat, you're going to get mu or P. But that's not true with S, because S is a bias estimator. So you get something close to this, but you won't get exactly sigma. So, good question. Now from there, we took that handout and went a little bit further. And one of the things you saw was that the sample mean was a random variable. That's certainly something that I would make sure I know. And that the mean of the sample mean is the same as the mean of our population. Now, we went a little farther than that in section 6.4. And in section 6.4, we saw that there was two conditions by which the sample mean had a normal distribution. So I'm going to leave that for you to look up. Rats. The mean of the sample mean is the population mean. Okay. So under what two conditions does X bar have a normal distribution? And there's two. I'm going to let you look those up from your notes. But you should definitely know those two different conditions. Now, let's see if we can't practice those and some of the implications from this. And let me go to my handout. SAM3 review. Let's go all the way up here. Yes, this one right here. This is a good one. You should fully expect something like this on your exam. So it says, when women were finally allowed to become pilots of fighter jets, engineers needed to redesign the ejection seats because they had been originally designed for men only. The ejection seats were designed for men weighing between 150 and 191 pounds. Weights of women are normally distributed with a mean of 171 pounds and a standard deviation of 47 pounds. Complete parts A through C below. All right, so the first one asks us, what's the probability that somebody who's randomly selected has a weight between 150 and 191 pounds? So let's take a look at that. So the things I want to write down here that are relevant. Thank you. So 171. And I got a couple of values that I want to sketch in as well. 150 and 191. I want to find the area between these 2 points on this normal curve. Now, there's a couple ways you can do this. I guess I kind of lean towards Google Sheets. The reason I do is because if you wanted to use StatDisk, you'd have to convert this to a z-score first. Remember how to convert something to a z-score? It'd be z equals x minus mu over sigma. You'd have to do that for both of these pieces of data, and then you'd have to find those areas, those corresponding areas in a different distribution. Okay, so let's do that in Google Sheets. Here we go. So I'll just start a new sheet here. Now the command that you want to use is norm distribution. Now all your Google Sheets commands start out with what? Equals. Norm distribution. And then you want the value, 191, and then the mean, which is 171. The standard deviation is 47. What comes after all that mess? True. Excellent. True. Bam. And so I get 0.66477, etc. And let me click back up here just to show people that that command there. So it's norm distribution, 191, 171, 47, and true. Okay, nice. But let's keep in mind what I want. I want the area between these. I don't want just the area to the left of 191, which is what I've got. So what do I need to do? Perfect. Well said. In fact, that's exactly how I'll do it here. So per suggestion, let me copy that. I'll paste it down here. And all I'm going to do is change this to a 150. And now I'll finish up by subtracting these two. So one more quick glance. Let's see here. I want this one. Let's see. Minus A2. There you go. And that's the difference. That's the answer that we want. You should get about 0.3373. I just hit Control C, and then down here, let me just delete this. You hit Control V, and then you want to go back up here and just change the one little piece of information that's changed, which is the 191 becomes a 150. And the reason we do that is because you found the area to the left of 199, and then the area to the left of 150. If I subtract off that area, I'll just be left with the area between those two. All right? So let's see, that was about, what, 0.3373? Is that what I said? Thank you. Now the next part is worth 6 points. This first part's worth 4 points. So where am I putting the emphasis on this problem? Yeah, on part B. All right, so let's take a look at part B here and see what's going on there. If 35 different women are randomly selected, find the probability that their mean weight is between 150 and 191. So we're not dealing with the same distribution anymore. Now we're dealing with the distribution of the sample mean for samples of size 35. So let's take a look here. This is X bar for samples of size 35. The important thing to start out with is, what's that distribution? Anyone? How about the mean of that distribution? Good. So you're sampling from this population. This mean here is going to be the same as the mean from its parent population, from the population that you're sampling from. Remember, because X bar is an unbiased estimator. So 171. Thank you. Someone else. The standard deviation has changed. What's the standard deviation now? Or how would I calculate the standard deviation? Awesome. 47 divided by the square root of the sample size, which is 35. Well done. Well done. And a couple people in the chat getting me that one. Good job. Now, if you do that, you're going to get about 7.94 something, I think. All right. I'll show you a couple different ways that we can calculate this new distribution, or calculate the probability associated with this new distribution. But one thing I want to point out, and that is, if this is about 7.94, which distribution is going to have a wider spread, the first one or the second one? Which one's going to be more spread out? All right, I got to vote for the first one. Yeah, the first one, right? Because it's got a bigger standard deviation. And standard deviation talks about how spread out your data is. So if I was trying to draw this to scale and draw it somewhat accurately, my distribution here should be skinnier. Now, I don't really have a good way of trying to draw this with any accuracy. So I'm just going to try and convey the spirit of what's going on here, though. So that's the spirit of it. This distribution is much tighter around its population mean, which is 171, as opposed to our other distribution. Here, things are more spread out. Here, they're more concentrated. So what that should mean is that more of the area should be between 150 and 191 in this distribution as opposed to our last distribution. It's tighter. More of that area is crammed closer to 171 and in our interval. Does that mean that the probability that we're going to calculate is going to get higher or lower? What would you guess? Is there going to be more area here or less area? I guess we'll find out. All right. Now, as far as calculating this one is concerned, there's two possibilities. Let me display both. And it's up to you which one you choose. Wrong one there. All right. I think the easiest way to approach this is to start by copying our previous one and then changing the standard deviation. Now, kind of the brute force way to change the standard deviation is to take out your calculator, take 47 divided by the square root of 35, and figure out that it's 7.94 something. So then just type in the 7.94, and then I'll copy that and put it down here. Except now I'm going to change that to a 150. And then the difference between these two, so equals this minus this. And I'll get back to that top one in just a second. So there's your top one. Now this isn't the one that I copied down. Let me show you the one that I would recommend that we do. And let me put that one over here. I'm just going to type it from scratch. Equals norm distribution of 191, comma, 171, comma. And here I need to put in my standard deviation. What if I just type in 47 divided by SQRT of, I don't know, 35? Yeah, make Google Sheets do all the work, right? Hey, Google's got enough money. You can work a little hard. So, comma, true, and then bam. Now, I should get something very close to what I got in column C. Maybe I do. Thank you. Bam. There you go. And then down here, let's just copy that down here and change this to 150. And then the last one is going to be the difference between these two, equals this one minus this one. Actually, I got that backwards, don't I? Did I change the wrong one? Yeah. Let me go back here. I should have changed that one to 191, and the one below should be 150. 150. There, the difference. You don't have to do this in 2 steps. If you wanted to do this all in 1 step, you could. To do this all in 1 step, let me show you how you could do that. So you could do, I'm just going to cheat a little bit and copy this first one down to get me going. This minus norm distribution of all that stuff, except change the lower limit. So I got to get rid of the equals sign. And then this needs to be 150. So just put it all in one command. Now maybe that's a little too long for you. That's fine. Whatever's convenient for you, that works for me. So exact same answer, both here and down here. Any preference? Do you like to do it in 2 steps or 1 step? Just out of curiosity. 2? All right. Seems like a lot of you are happier doing it with 2. That's fine. All right. That's unanimous then. So thank you, Sonia. Cool. So that second part, that's the key thing. You're using the central limit theorem in that one. And that's something that I really want you to know, because the conditions under which normal distribution occurs, especially with a sample mean, are going to help us, or are going to be part of a lot of what we do in this course. So that second problem is a good one. Okay, let's keep going. Let's keep going. Let's take a look at what's next in terms of our handout. So that was section 6.4. Let's move on to section 7.1. So it says a magazine poll of 2,000 adults who were asked to identify their favorite pie. Amongst 2,000 respondents, 12% chose a chocolate pie. All right. They needed more Michigan people in their sample. So let's go back here. It's 12% with a margin of error of 5 percentage points. So let me copy down the relevant information here. So this is section 7.1. And we had 12% plus or minus 5%. Quick question for you. What was the point estimate of the percentage of people who like chocolate pie as their favorite pie? What's the point estimate? Say again? 12 over 100. Nice. I like that. Yeah. Now remember, this is in the form of p hat plus or minus e. And that p hat right here, that's your point estimate. That's your best guess as to the percentage of people who think that chocolate is their favorite pie. So it's your point estimate. What's this E term here? It's your margin of error. So you know going in that p hat is probably not going to be exactly the right number. That the true proportion of people who think that chocolate pie is the best is not exactly 12, but it's probably within 5% of 12. So how would that look? Well, typically we write these things as p hat minus e to p hat plus E. Instead of a 2 there, let me write it a little differently. So let's say this. The true value, P, is probably somewhere between P hat minus E and P hat plus E. In other words, this is our confidence interval. So that'd be 0.12 minus 5%, 0.12 plus 5%. So that gives me 0.07 is less than P is less than 0.17. So somewhere between 7 and 17%, that's where we think that the true population parameter lies. And that's your confidence interval. And you should be able to go back and forth between, say, something like this and something like this, or vice versa. You should practice finding these things with StatDisk. There's an example on your handout, and I'll let you finish that one up. But are we okay here? Now, we find confidence intervals for all kinds of different things. So far in this course, we find confidence intervals for population proportion, population mean, and population standard deviation. So let's keep on scrolling down in terms of our handout. In working with those things, one of the things you might encounter is the need to find a critical value that corresponds to a given confidence level. So in this case, our level of confidence is 82%. I think I might change that up a little bit for us, make that something different. That way, well, I guess it doesn't matter. We're going to find z sub alpha over 2 for all that. Now, this involves and implies a lot of understanding of different things. It's a short question to ask, but there's a lot of layers to this onion. So, first of all, our level of confidence is 1 minus alpha. Or looked another way around, alpha is 1 minus our level of confidence. And in our case, that was given to be 0.82. Okay, good. Now something else that we need is we need to understand and remind ourselves what z sub alpha over 2 is all about. And the short story of what that's about is that it's a point on the z distribution with that much area in the right tail. So the point on the z distribution with 1 minus alpha over 2 of the area, actually no, pardon me, not 1 minus that, sorry, I'm thinking ahead a little bit, with just alpha over 2 of the area in the right tail. And I can't emphasize enough that it's the area in the right tail. Unfortunately for you, most of the tech ways that we have to get areas are going to rely on looking at the area in the left tail. So that's kind of a little bit of an annoyance. It's a discrepancy. They want the area in the right tail, but you have to look up the area in the left tail to get it. So just be advised for that little hitch beforehand. So alpha in this case is going to be 0.18. So find z sub alpha over 2 really means z sub 0.18 over 2. Unless you're really confident about this, take out 0.18, or take out your calculator and divide 0.18 by 2. You don't get 0.9. It's 0.09. So I want z sub 0.09 for that. You don't want to get this run wrong just because you made an arithmetic error. That would be bad. Let's draw that. See what we can come up with. 0.09, that's going to be the area in the right tail. So should I draw that to the right or to the left of 0? Has to be in the right tail because there's only 9% of the area. Half of your area is to the right, so I have to be further than that point. So somewhere out here. So 0.09, z sub 0.09. Now, like I said, if 9% of the area is in the right tail, you're going to have to look up how much of the area is in the left tail. So how much of the area is in the left tail? Yeah, it's going to be 1 minus that, right? So it's going to be 0.91 is going to be the area in the left tail. So 0.91, that's the area in the left tail. Now I'll show you 2 different ways that you can get that area. Since we're already on Google Sheets for some of this, let's start with Google Sheets. Your command is no longer norm distribution. What command do I want to use? Nice, norm inverse. All right, so norm inverse. The area in the left tail is 0.91. The mean is 0. The standard deviation is 1. So norm inverse of 0.91, comma 0, comma 1. So from that, I get 1.3408. So equals norm inverse of 0.91, comma 0, comma 1. Or you could get that from StatDisk. Now to get it from StatDisk, we're going to go back to our normal distribution under the probability menu, under the analysis menu. So let's find that. Analysis, probability distributions, normal distribution. So we've got an area and we want to find the z-value. So let's put that area in here. It's 0.91. And what I like about StatDisk in this case at least is that it just gives you like everything. And of course what we want is right up here, 1.3408. So you're free to use either one. That's why I showed you both. Yes. So analysis, probability distribution, and then normal distribution. So the second one is for StatDisk. The first one is for Google Sheets. Yeah, pick whichever one you want. There or here. Okay, nice. How are we looking on that one? Doing okay? Let's keep it rolling. So here in this next one, you could type in some information here. So you'd have 2,581 subjects were selected. That'd be your N. This is your X. You could input that information to construct a confidence interval. So that I would suggest you do on StatDisk, analysis, confidence intervals, proportion, 1 sample. That's what that is. And then you type in your level of confidence, sample size, and number of successes, and go from there. And when you're done, make sure you practice saying your conclusion in words. Yeah, I'm going to move on to the next one. 7.2. 7.2 is when we started discussing confidence intervals for a population mean. That required us to introduce a different distribution. Does anyone remember what distribution that was? It was the T distribution. This name comes to us from William Gossett Jr. of the Guinness Brewery. All right. Now, one of these is not a requirement for constructing a confidence interval for the population mean with sigma known. Actually, this is... let's take a look at these things. Now, the requirements, the ones that we're going to worry about, is that our population has a normal distribution. Now, that can happen in a couple different ways. It can happen because you have a large enough sample size, or because you're sampling from a population which already has a normal distribution. Either way, that population is going to be normally distributed. So, cool. We're good there. All our sampling methods are going to require a simple random sample, so that's true. And you can only construct confidence intervals for something that has a quantitative value. So if I rule out those three, then by process of elimination, this one's left. By the way, as a reminder, it's really rare that you would have a confidence interval for the population mean. Somehow you don't know what the mean is, but you do know what the standard deviation is. That's just not going to happen. This is one that I'll let you play with. But let's cut down to this one. And even though I have the data on this one, we can do something interesting for this one. So let's take a look at this. It gives us 2 confidence intervals for the pulse rates of females and the pulse rates of males. So pulse rates for females has a confidence interval between 71.9 and 80.1. Let's write some of these things down. So 71.9 is less than mu, so F is less than 80.1. And for men, it was 62.7 and 72.9. No, not 72.9, 70.9. There we go. 70.9. There's something interesting about these confidence intervals. Even though we don't have the data, there's something that I want to point out about this problem. Now let's draw this. All right, so here, and let's put in a few hash marks on this as well. So this will be 60, 65, 70, 75, and 80. Let's draw our different confidence intervals. The first one that I'll draw is up here for the ladies. That's between 71.9 and 80.1. So that's here. The second one is between 62.7 and 70.9. So, yeah, about here. Let me kind of sharpen that a little bit. 62.7, 70.9, and then 71.9 to, and that's not exactly very accurate, but that's good enough, 80.1. There's one striking feature about these confidence intervals that I'd like you to see. Can anyone tell me what it is? What's interesting about these confidence intervals? Perfect. Thank you, Heather. They don't overlap. And that means that these populations are most likely different. Because if they weren't different, then their confidence intervals should overlap, but they don't. So you probably have two different populations that you're working with. In fact, I think that the conclusions that they lead you to include that. The confidence intervals do not overlap, so it appears that adult females have higher mean pulse rates than adult males. Perfect. Now, I do trust that if you're given the data, that you can find a confidence interval. For that, you're just going to go to StatDisk, plug in the data, it'd be analysis, confidence intervals, mean one sample. And you either use summary statistics or click use data if you actually have the data. Will we ever be putting in something here for population standard deviation? No. It's just not a realistic possibility that you would somehow know the standard deviation and not know the mean. Cool. Let's keep going. Section 7.3 required us to do a new distribution. What was that distribution that we used to estimate standard deviations and or variances? What was that distribution called? Does anyone remember? Yeah, well done. Well done. All right. Let's see. Here. Yeah, somebody. Yeah, that's actually the bonus question is what does my daughter call it? And she calls it chi-square. All right, so the thing about the chi-square distribution is that it's not symmetric. It changes with degrees of freedom, just like the t distribution. So this is your chi-square distribution. It starts at 0 and then moves out towards infinity, so it can't be symmetric. Now, what we're going to look for sometimes, what you could be asked for, is to find what are called chi-square sub L and chi-square sub R. Now, let me show you what those values are. Show you what those values represent. So sometimes I want to create a confidence interval that puts, a certain percentage of the area in the tails. And that percentage of the area is going to be related to my level of confidence, or you could also think of it as being the level of significance. One is just one minus the other. But these are the values that I'd want to get. This one's called chi-square sub L, and this one's called chi-square sub R. And the area in the tail, I'm going to want to be alpha over 2 in both tails. Why alpha over 2? Because I'm taking that area that comes from my level of significance and splitting it up into 2 tails. So let me remind you as to how to find this. And what I'll do is I'll do this for an example similar to the one that's in your handout, but I'll leave you the one that's in the handout to work at home so that you can practice this, because practice makes permanent. So the one in the book asks us to do something for an 80% level of confidence. A more typical level of confidence is a 90% level of confidence. we're going to use the same n, which is 29. So let's do that. N equals 29. Degrees of freedom, I'll leave as unknown. Alpha, I'm going to set at 5%. Now, if I have n is 29, how many degrees of freedom am I going to have?
Is it a -1?
Yep. Just like the t-distribution, n minus 1, so it'd be 28 degrees of freedom. Thank you. 28 degrees of freedom. Now, I need to find the point in this distribution with alpha over 2 of the area in the right tail. So let's figure out what alpha over 2 is for us here. Alpha over 2 is 0.05 over 2, which is 0.025. That's the area in the right tail and the area in the left tail. Let's see how we can find those values. Well, where do you think is a good place to go find those values is? StatDisk. Yeah, absolutely. In fact, I don't know if Google Sheets does it. I think they do, but it's much easier on StatDisk. This is pretty nice. It is so much better than the tables you used to have to use in this course. So analysis, and then probability distributions. And there's our chi-square distribution, aka chi-square. Let's select that one. Notice what it's asking for the degrees of freedom. Do not put in n. If you put in 29, you're going to get the wrong answer. We need to put in 28. And take a look at what you're given. You can either put in the chi-square value and get the area, or put in the area and get the chi-square value. Which one of these do we need to do? First one or the second one? Second one, yeah. Good job. A few people in the chat and somebody here as well. So we need to do the second one. So the area to the right, well, that's pretty easy. For at least one of these, that's 0.025. So I get 44.46. Now, which one's that going to be? Is that going to be chi-square sub r or chi-square sub l? Which one gets the 44.46? Yeah, chi-square sub r. Because that's the point with 2.5% of the area in the right tail. So 44.46. Well, it's by what you put into this to get out of it, your area. I wanted the point with 2.5% of the area in the right tail. And that point is my chi-square sub r. Let's see here, right there. Now the tricky thing is, I want this one on the other side of the distribution with 2.5% of the area in the left tail. But that's not the way that StatDisk works, is it? StatDisk wants to know, well, what's the area in the right tail? I don't care what's in the left tail. You tell me what's in the right tail. So if 2.5% of the area is in the left tail, how much of the area is in the right tail? No. 1 minus that. Good. And 1 minus that is going to be 0.975. So that's the area that we need to type in to get the other value from our chi-square distribution. So see if you can't find that value. I'll give you a second or two to look at that. If you get it, throw it in the chat. And I'll also walk around here, see what you get. No, it's 0.025, so 0.975. So you're right, it's 1 minus 10 moves. Yep. So if 2.5% of the year is in the left tail, how much is in the right tail? Sure. 1 minus 0.025, and that tells you how much of your is in the right. Okay, I didn't see too many people here in the chat, so let me try and go through this one carefully. Keep in mind that if there's 2.5% of the area in the left tail, then we have to figure out how much of the area is in the right tail. And maybe it's worth just a second or two to type it in your calculator, because I see people making mistakes on this every now and then. So 1 minus, get out of my way here, 0.025. Oh, there you go, 0.975. So 0.975, that's how much of the area is in the right tail. And why do I need that? That's the way that StatDisk works, is you got to type in the area in the right tail. So I need that 0.975. Let me put that in. So 0.975. And I should get something less than the 44.46 that I started out with. In fact, you get about 15.31, we'll call it. So 0.15 or 15.31. Nice. Yes. Okay. So a lot of people in the chat getting that one right. Good job. Thanks for keeping up. Any questions on this before I move on, though? I know that there's several of you that are a little bit lost or struggling. If there's something I can do to help you out now, let me know. Keep in mind that when you're watching videos, if you need to, you can pause, rewind, try and get some more help, or just take a look at things again, because I know sometimes this goes a little bit fast. Let's continue. So you've got one to practice at home right here with an 80% confidence, level of confidence, and 28 degrees of freedom. You find those chi-square sub L, chi-square sub R. We're kind of running low on time, so let me just kind of look at this one and again point out the important part of this and remind you a little bit about standard deviation. These are the waiting times in banks for two different banks with different lines of customers. One has one line that services 3 tellers, and the other one has 3 tellers with 3 lines. And they want to look at the standard deviation of their waiting times. Now, what does the standard deviation measure?
How far away you are from
Beautiful. I wouldn't change a thing. How far you are away from the mean. On average, how spread out your data is. Now, we got these 2 confidence intervals for the standard deviation of waiting time for bank A and for bank B. What do you notice about those confidence intervals? Let me kind of zoom in a little bit here. So here it is for bank A, here it is for bank B. What do you notice about those 2 confidence intervals? They're definitely very different. All right, a little more than double. Do they overlap? No, they don't. So they're coming from different populations is what that's suggesting. Meaning that bank A has a standard deviation of wait times that is much smaller than bank B. Now, if you're the bank manager, which one do you want? Do you want lower standard deviation or higher standard deviation of waiting times? Probably lower, but why? What would that imply if you had lower standard deviation?
The wait time's shorter.
Not necessarily shorter,
More
but
efficient.
yeah, there's more efficient. There's less variability in customer experience. You're not going to have somebody getting through in 2 minutes and somebody waiting 10 minutes. Everyone's going to have the same kind of experience. I don't know. Have you ever been in a line someplace on the freeway or in the grocery store and like, man, I picked the wrong line. Somebody there is like paying with pennies or doing something obscene that takes like forever. You want people to have the same experience, one versus the other. You don't want to see that one person getting through the line just like that while you've been there for 10 minutes. That'd be frustrating. So, okay. Now, it doesn't necessarily apply that one set of wait times is shorter than the other wait times. In fact, if I remember this problem correctly, both banks have the same average wait time. So it just comes down to the standard deviation of those two banks in terms of their wait time. And yeah, you want to have more consistent wait time. That brings us to section 8.1, p-values and probability, p-values and hypothesis testing. Which of the following is not true about p-values? We're going to do this one again by process of elimination. The p-value is an area, the p-value is high, the null will fly. In fact, a couple of these things are things that I've said in class. Can anyone pick out the two things that I've said in class talking about the p-values? Yeah, B and D. If the p-value is high, the null will fly, meaning you're not going to reject H0 if the p-value is high. If the p-value is low, H0 must go. Or the p-value is low, the null must go. So B and D, we can throw all those out. So if you're trying to hedge your bets, it comes down to A or C. Now let's look at A. Is the p-value an area?
Yes.
Absolutely. Yep. P-value is an area, so that means the false one is C. And C wouldn't even make sense to you because we're not really taking that approach to our hypothesis testing, so great. Now let's keep going. The Erickson method is one of several methods claimed to increase the likelihood of a baby girl. In a clinical trial, the results could be analyzed with a hypothesis test with the alternative hypothesis of P is greater than 0.5, which corresponds to the claim that the method increases the likelihood of having more than 50% of your babies are girls. If you have an interest in establishing the success of this method, which of the p-values would you want to see? 0.999, 0.5, 0.95, 0.05, 0.01, 0.001. Which p-value would you want? Well, let me do this much for us to begin with. We're looking at testing this claim. That is, claim that p is greater than 0.5. Is that claim going to be part of your null or alternative hypothesis? Yeah, thank you again. That has to be part of your alternative hypothesis because it doesn't contain the possibility that it could actually equal 0.5. Now, we've gone over this before, but on my stat lab, that would be p equals 0.5. What kind of a tail test is this? Left tail, right tail, or two tail? This points it to be a right tail. It's pointing in that direction. It's a right tail test. So it's going to be a right tail test. It's going to correspond to some area in the right tail. And that's what your p-value is. Thank you, Sonia. Now, if you want to establish the claim here, your original claim that this method is effective, you want that p-value to be as small as possible because the p-value represents the probability of making a type 1 error. That's what the p-value is. And the smaller that is, the smaller the chance that you've made a type 1 error, which is rejecting the null hypothesis when it's true. the p-value represents the probability of a type 1 error. And a type 1 error is the probability, or not, it's not the probability. The type 1 error is rejecting H naught when it's true. Zach? Yes, because you want to make that probability of a type 1 error as small as possible. So, yeah. Okay. One or two more, depending on how much you have stomach for. I know we're a little bit past time. If you got to go, you got to go. I understand. Actually, we'll do two more. And that'll exactly finish where I want to go. Claim the standard deviation of pulse rates is more than 11 beats per minute. Now I'm going to help you out on this because I want to get you out of here. So when you're talking about claims, you want to write those in terms of a population parameter. If you write S, or if you write X bar, or if you write P hat, you're going to lose points. They have no place in a hypothesis test. Now in this case, the claim is that the standard deviation is greater than 11. Okay, sigma is greater than 11. If you set up your HO and your HA, then this has to be part of my alternative hypothesis because that sigma is greater than 11. The null hypothesis is sigma is less than or equal to 11. Of course, WebAssign, or not WebAssign, but my stat lab would call that sigma equals 11. What tail test is this? Left tail, right tail, or two tail? It's going to be a right tail test. Say again?
Like if there's a greater than sign, can you just already assume that it's going to be a right tail?
Generally, the right tail, left tail stuff works like you would think as long as your parameter is on the left-hand side of your inequality. Because I could write this is equivalent to 11 is less than sigma. So if I wrote it that way, it's still a right tail test because it's equivalent to this, and that's a right tail test. So I guess yes, as long as you're putting the parameter on the left-hand side. So we got a test statistic of z equals 2.33 obtained when testing a claim that p is greater than 0.8. This is actually the one I thought I was doing just a minute ago. I'm sorry. So our claim is that p is greater than 0.8. That's a claim about a hypothesis for a population proportion. Now that claim is going to be part of our alternative hypothesis. So let's put that in HA. Mu is greater than 0.8. That means HO is at, I said mu. P is less than or equal to 0.8. Is this a left tail, right tail, or two tail test? It's another right tail test. It's pointing in the right direction. So the p-value is just this area. And I'm not going to take the time to look up this p-value with you. It's just going to be 0.00990. That's that area. You can get that from StatDisk or you can get it from Google Sheets. Now, the question is, with that p-value, are you going to reject H naught or fail to reject H naught? What are you going to do? What's the rule? In fact, it was actually kind of part of one of our problems earlier, where we did the eliminate a couple things. If the p-value is low, finish it up the sentence for me. H naught must go, right? So if this is less than the value of alpha, then you're going to reject H naught. So that would be your decision here, is to reject H naught. Yay. All right. So the last thing that you can expect on your exam would be something that I left off of the homework. And that is type 1 and type 2 errors. So we'll finish up with that. And my original claim is going to be that border collies have a mean weight of 42 pounds. So original claim is that H naught, or that mu equals 42 pounds. Now, where's that original claim going to go? In HO or HA? It's going to be in HO. Your alternative has to be like the complement of that. Like, all right, if this is true, then the opposite could be, well, it's different than 42 pounds. So let's remind ourselves what a type 1 and a type 2 error are. Type 1 error is to reject H naught when it's true. Reject H naught when it is true. Now, I will give you these definitions on the exam. Do you remember why? Because I'm a nice guy. You missed a chance to get some extra credit there. All right. Type 2 error is to fail to reject H naught when it is false. So those are your two definitions. And let's see here. Give you a second to copy that. There we go. And here's two handsome doggies dressed up for Halloween. Yay. All right. So what would a type 1 error and type 2 error be here? The reason I give you these is because I don't want you to give me a definition. I want you to interpret it in terms of what this means as far as the problem is concerned. So type 1 error, I want you to tell me what's true and what your decision was. So what is true about H naught? So that's the first part. And the second part is, what was your decision? Your decision. Now, I have a hard time grading these because I really got to parse through what you write. They're not that fun, but let's go for it anyways. Type 1 error. Start by saying what's true. And in this case, what's true, if you're making a type 1 error, is that H naught is true. So it is true that border collies have a mean weight of 42 pounds. So that's what's true. That's the first part. The second part is you got to say, well, what was your decision? Now, if you've made an error, then your error was that you rejected that. So the second part is, but the data rejected that claim. The data rejected that claim. If you're making a mistake, then these two things should be pointing in opposite directions. What's true and your decision should not match. Type 2 error. That means H naught is false, but we didn't reject it. So let's see if we can't state that. And I would write it like this. The claim that the mean weight of border collies is 42 pounds is false. So that's what's true about H naught, is that H naught is really not accurate at all. It's false. But that's the truth about H naught. Now, what was our decision? Our decision was we failed to reject that. So, but the data failed to reject that claim. And nowhere in here did I use the word hypothesis, null, or alternative. I didn't give you a definition. This is just describing in words what happened. Okay? And there's two things that I want. I want you to tell me what's true and what your decision was. So, nice. All right. Hats off to you for sticking with me for an extra 10 minutes. It comes at no additional tuition costs, so that's a good thing. We're helping fight inflation here. Test is on Wednesday. Good luck, and see ya.